You'll have today homework 3 that was a bit delayed. I wanted to see a bit what exactly I want to add to linear programming. We have a few venues that are spamming from linear programming, and we can decide today which direction to go. So I changed the slide quite a bit. I want to be a bit formal about the proof of the linear programming, and along the way to teach you about expectation and a sum of expectation that we'll use in several algorithms in this course. And then I'm going to make a quick jump to another algorithm that use backward analysis namely the closest pair algorithm. But hopefully we'll have time to finish all of it today. And what I'll also probably do is use the targeting the fact that some of you, that will be the only algorithm course that you'll take. So probably I'll spend some time talking about integer linear programming and linear programming in higher dimension. How do we handle them? And show some application, because it's just fantastically useful, powerful tools for many applications way beyond computational geometry. So it's since we are already covering linear programming, it will be a small addition to the course that gives you a lot of tools that you can use later, either if you are going to research or you are going to the real world. Either case, it's very useful. Questions about anything at the meantime? Excellent. I want to speak about expectation and about random variables. Let's think that we are spinning a roulette. A roulette is something that looks like this, a wheel with slots inside. That's a roulette. And during the roulette, we are generating a random variable. So X over here is a random variable, which to me, when I was introduced to it, was unbelievably confusing term. The term of why is this a variable? The name doesn't fit anything that I intuitively try to understand. So we are using the term variable because that's a term that the whole literature is using. But think about it as a function that takes the position of the roulette, the number from the roulette, which we'll called a state or an event, and it is assign value to it. And the first random variables that I can think about the roulette, about a number or a function that takes a random variable, despite the named variable, it is actually a function. In the sense that both function as math function and function as a C function. It takes a state of the roulette as an input for time being, and it spits out some number according to which number did you hit in the roulette. Maybe any of the English speaker, what are we doing with the roulette? We are tossing rolling dice. We are tossing a coin with the roulette. We spin the roulette. What happened after experience and the result that came up? Does it have a term? Which numbers did we hit? No gamblers around here. Okay, let's think about it as a number that we hit, the number that the ball of the roulette landed up on. So we are taking a number from the roulette, and the numbers that we hit, and we assign some number to the number that we hit. For example, it could be exactly the number that we hit. The roulette, I think that there is a difference between American and European. The one that I had in the picture of the slide had 36 slots. So we are getting a number between 1 and 36. So by itself, it's a random variable. We have a set of possible events. Maybe an event would be we hit the number 1, we hit number 2, we hit number 3 in the roulette. And we are asking which number it is. So that is one example of a random variable, but I can also define a different random variable. I'll say here is another random variable, again, a function of the roulette, of the numbers that we hit in the roulette, and this function will say, we'll call it x, and x is 1 if and only if the number that we hit in the roulette is even. Otherwise, x will be 0. And most, if not all, the variables that we'll use in this course will be Boolean variables. Okay, I have two chats that I ignored. Sorry about it. It's recorded on, we are recording it on, can also record it over here, but it's also recorded. Twitch, first Twitch stores the video in a much better quality, and your public information doesn't appear on Twitch, so there is no fear of your names appear. So if you want to watch a video there, and it's also a bit easier to edit. The editing tools that comes with Pinapto are horrendous. So if I want to edit a bit, remove dead minutes, similar like this, I prefer to do it in Twitch. And then after editing, I am uploading it into D2L, and the D2L is fine, except that it's compressed very aggressively. So both the voice and the picture degrade significantly. Yeah. So, and the only downside of watching the live lecture in Twitch is that you are getting it 40 seconds later. So, and I don't see your chat if you ask questions out there. No, I don't always see your chat if you're asking questions. So, back to business. So we have a Boolean variable, and Boolean variable I found at least much easier to understand with other variables, because we'll think about him as just a flag. A flag is either off or on. Something happened or something did not happen, according to the result that I got in the roulette. So here I'll define a random variable named x, a function that takes something from the roulette, and I'll say this function x will be equal to the 1 if the number that we hit is 2, 4, 8, etc. And if the number that we hit is odd, 1, 2, 3, 1, 3, 5, 7, then x will be 0. And let's say that if x is 1, that is a ball of the roulette hits an even number, then we earn $5. What is our average earning if we'll repeat some experience a million times, very large number of times? And then we'll ask what is the expected earning that we are having. What will be an expected is just an attempt to say average, but in more mathematically correct terms. It will have an exact formula for what is expected term. So what is the average value? So how much do we earn? We earn, if x equals 0, we earn nothing. If x equals 1, we earn $5. So what we are earning is x times $5. If we did one experiment, how much are we getting? We are getting x, which is 0, 1, times $5. If you were lucky and the ball hit an even number, then you'll get $5. If the ball is if you're unlucky, you got 0 times $5. And so what we are earning is 5 times the probability that x is 1. In the roulette, if the roulette is fair, you have 36 many numbers. The values that you can get are 1 to 36 many numbers. Half of them are even, half are odd. So the probability that x is 1 should be half, if I'm not making some stupid mistake. So we are getting on average $5 times the probability that we are earning it. So on average we are getting to $0.5 on average. We will repeat it billion times, and 10 billion, 20 billion, billion, and each time asking what is the earning divided by how many games did we try. And of course, that would be the average value. It would be the expected value of x would be x itself times $5, which is nothing but 5 times the probability that x equal 1. Any questions so far? Makes sense, right? That's our average earning. Now, if I'll use variables that are not Boolean, then the formula of expectation is a bit more complicated. Just for the sake of completeness, I'll show it only once. If x would be, for example, 1 if we hit an even number, x equal 2 if we hit 20 or 21 or 22, and x equal 3 if we hit if hitting 30, for example, then I can what happen? No, I don't want these numbers because they are not. Now you'll ask what is actually. Sorry. Let's make it 23 and 25, and x equal 3 if we are hitting 29, and 0 otherwise. And if I want to ask now what is the expected value of x itself, x is not a Boolean variable, just for the sake of completeness, I need to look at a sum sigma of I goes from 0 to infinity of I times the probability that x equals I. If just a formula, and it makes sense if we think about it as how many dollars we are getting in each one of the cases. If for even number we are getting $1, for if we are hitting 23 or 21 or 22, we'll get $2, and if we are hitting 3, then we'll get, if we are hitting 29, then we'll earn $3. Then we have this infinite loop from which, what will I ask? What's the probability that we are getting 0? What's the probability that we will get 0 right here? We can debate about it for a moment, but we see that the contribution to this sum, the contribution of the case I equals 0, is 0 times something, the probability of x equals 0, which contributes nothing because of the 0 right here, so I don't even bother to compute it. I'll ask, what is the probability that x equal 4? What's the probability that x equal 4? Well, x is, we can declare what is a random variable any way we want. There is no correct or incorrect way to define random variables. You just need to assign to whatever happened in the roulette, you need to assign some numerical value, and you can do it any way you want. So if that's the way that I assigned the values, then what's the chance that I hit some event that leads me to I equal the 2x to be 4? Never happens. So the probability of it is 0. What's the chance that I equal 5? Probability is 0. These are the only 4 values that x can get. It will be either 1 or 2 or 3 or 0. So all I need to ask here is, what is the probability that x equal 1? That is, it is 1 times probability that x equals 1, which is exactly 0.5, plus 2 times the probability of x equal 2. What's the chance that this happens? That x equal 2? Help? There are 3 numbers over 36. So the probability that x equal 2 is 3 over 36, which makes it, I think, 1 over 12, times 2, plus 3 times probability that x equals 3. The probability that x equals 3 is exactly 1 over 36. So it's 3 times 1 over 36 plus 2 times 1 over 12 plus 1 times 0.5. This is the expected earning if this will be your earning after each experiment. So this is the formal definition of what is the expected value for a random variable that is positive and integer. If it was a float, I had to replace it by an integral, but I think that we will not need it in this course. People, are we good with what is a random variable? Okay. Now you also see from the summation that if x can only get a value that is either 0 or 1, that is, x is Boolean, that is, x is 1, say, if I get even number, x is 0, then what happened with this sum? I sum up the case of 0 times probability that x equals 0, I don't care what it is because it's 0, plus 2 times probability that x equals 2, never happens. 3 times I equal 3, 3 times probability that x equals 3, never happens, etc. The only element, if x is Boolean, if x is either 0 or 1, then e of x is just the probability that x equals 1. Good? Because that's the only element that is left here, and there is a 1 standing here, which is the case of I equal 1. I want to continue a bit with the roulette, and now I'll define 2 random variables. X equals 1 is one random variable, again, one function that receives any value only after you make some trial with the roulette. You spin the roulette once, and then you know if x is 1 or equals x is 0, depending on the result. So let's say, as before, x is 1 if and only if we hit n even number in the roulette. And let's define another random variables, y, which will also be a Boolean random variable. Y equals 1 if and only if we hit a number which is divisible by 3. That is, if we hit 3 or 6 or 9 or 12, 36, then y equal 1. And as before in both these cases, since they are Boolean variables, otherwise x equals 0, and otherwise y equals 0. Okay, I will slowly will get rehabilitated from saying the otherwise part. It will be clear any moment that I'll say Boolean random variable. That is, variables that can be either true or false, 0 or 1. Now, we saw beforehand that if I'm earning $5 if x equals 1, and let's add now earning $9 if y equals 1. And I am making one experiment with a roulette, and what will be my average earning? If I just hit the roulette, I just made the experiment, so now there is value to x and there is value to y. What is my earning from both these? If somebody is so lucky to give me this number, or I'm so lucky that somebody wants to give me this number, then what I'm earning is x times $5 plus y times $9, right? That's are my earning from one time that I ran the roulette. I'm getting $5 if x is 1. I'm getting $9 if y is 1. So y is 0, I didn't get anything. Y is 1, I got $9. And what I'm getting at the end, after the experiment, is possibly 5 plus 9. If I hit a number that is both divisible by 3 and an even number, 6, 12, and so on, or possibly x is 0 and I hit only 9, or possibly x is 1 and y is 0, so I'm getting only 5. And I'm repeating this experiment million times, so I'm asking what is the average, or more precisely, what is the expected value of these two numbers? What is the expected value of the total sum? What will I earn if I'm running it 10 million times? And it looks a bit tedious to think about it, because now I need to think about what is I'm getting $5 with probability of that I'm only getting 5, x is 1, but y is 0. Right? And in some cases, I'm getting $9 times probability of x is 0, y is 1, plus possibly I'm getting both $14 times probability of x is 1, y is 1. And I'm getting $0 with the probability that none of these cases happens. So that's one way to think about this expression. But I can think about this expression as, let's think about all the relationship of x is 1, y 0, x is 0, y is 1, that if they are independent of each other, which they are actually not. What I want to show you is a very strong formula that we are going to use several times. So big lemma that comes from probability, E of if x, y are Boolean values and a and b are constants, then the expected value of x times a plus y times b, this $5 and $9 are what a and b are, is just the expected value of x times a plus the expected value of y times b. But what did we say about Boolean, which actually I can write down as a times the expected value of x to be 0 or 1 plus b times the expected value of y. But we said that x and y are Boolean variables, so their expected value is just 0 times the probability that they are 0, which doesn't help me, plus 1 times the probability that they are 1, so it is a times probability that x is 1 plus b times probability that y is 1. Right? So, and that is quite surprising, because I don't care one bit about how I get x and y. Maybe I get them in the same experiment. Maybe it's two different experiments. Maybe they are depending to each other, or maybe they're exclusive. Maybe y is only I hit an odd number and x is only I hit an even number. Doesn't matter one bit what the relationship between x and y. They might be independent, they might negate each other, be complement, only one of them happens. If one happens, it increases or decreases the probabilities that the second one happens. We don't care. Every time that we see an expression of this type, Boolean times something plus Boolean times something, we'll just think about it as, and the rule that we are using is actually using two rules here. The first rule is says that expected of sum equals sum of expectation. Don't forget this formula. Expected of the sum of any expression equal to the sum of the expectation of the independent events, of the separate events, each term independently, the expected value of this plus the expected value of this. And the other rule that we used over here is that E of constant k times x, every time that I see a constant inside the expected value, I can take k to be outside the expected value and say that it's just k times e of x, where k is any constant, k for constant. Yeah, so k is coming from constant. So every time that you see a constant, you can write it down before the expectation sum. Okay, let's see if you'll like it. That's my son found it somewhere, that the B in the word Titanic, the B in the word Titanic is for buoyancy. Okay. Should I repeat? The B in the word Titanic is for buoyancy. Okay, let's get back to our slides. Here is the roulette. Here is an example. X and Y are two random variables. I want to estimate the expected value of X times a constant plus Y times a constant. And the big rule of expectation of the sum is the sum of expectation. Just tells me that the expected value of X times A plus Y times B is nothing but A times E of X, which is in terms A times the probability that X equal 1 plus B times probability that Y equal 1. Back to our algorithm, back to our linear programming. To refresh your notation about what happens, we are adding the constraints, adding age 1, then age 2, then age 3, all the way up to age n. And I'm sorry, I only start at age 3, then I'm adding age 4, adding age 5, inserting age 5 all the way up to age n. The reason that I start in 3 is that the algorithm starts by picking two half planes and using them to give me what is the and use them to determine the first solution. And let's say that I already am inserting n constraints already, that I have just inserted the last constraint, age n. And I am asking what is the probability that Vn is different than Vn minus 1. What is the probability that Vn is not Vn minus 1? To remind you the notation, Vn is the minimum point, the lowermost point that is satisfied by all the n constraints. Vn minus 1 was the optimum when I only had, let's write it down, Vn minus 1 is opt of in age 1 intersection age 2 intersection age students. Vn minus 1 is opt in the modulus of constraints age 1 intersected age 2 intersection age n minus 1. That is, while Vn is a opt in the intersection of all the half planes, including the nth one. So this is Vn. And remember, the algorithm has, what did the algorithm do in the last step? I added, say, age n, or possibly this was age n, I'm not sure. I added age n, and now I have two options. If Vn minus 1 is inside age n, if this condition happens, then I don't need to do any work when I added age n, right? If the previous solution is already inside age n, then I can stop the algorithm by just saying, yes, I checked that Vn minus 1, whatever was Vn minus 1, the very same point, is inside age n, and we don't need to work at all. So it just takes a constant time. Or if Vn minus 1 is not in age n, then two things happens. One thing is that if age n violates Vn minus 1, the optimum that we had without age n minus 1, then two things happens, and you need to realize both things. They are both quite essential for the analysis. One thing that happens is that we need to solve 1D LP, one-dimensional linear programming, because we are sure that the solution is on LN. LN, remember, or Li. Here is Li. The skin is a boundary of age I. So I'm solving the one-dimensional linear programming, looking at the line Ln with the half planes age 1 up to age n minus 1. Just to remind you where we were before. That was one thing, and that takes time. How much time does it take? If I have n minus 1 constraints, this takes theta of n time, right? Because I need to handle all these half planes, compute their intersection with Ln, and so on. So that takes linear time. That's one thing that happened in this case. And the other thing that helps us in the analysis is that the new solution, that is Vn, must be on Ln. Must be on not only inside the plane that age n defines, but actually on Ln itself, on the line that bound Ln. That is Vn, the new optimum solution. And notice, the new optimum solution doesn't care what be about in which order we are inserting the half planes. There is no careless about what, when I'm asking what is Vn, Vn is a solution to the whole linear programming with all the constraints. Doesn't matter at which order I inserted. Doesn't matter what decision the algorithm did. You have to look at all the intersection and look at the lowermost vertex if your cost function is to go down. However, the question of is Vn equals to Vn minus 1 or not, that is, did I spend a lot of time or very little time, this question definitely depends on the order. Because if Vn is different than Vn minus 1, then Vn, the new optimum solution, must lie on the line Ln. That is, not only inside the half-planes, but touching the line Ln itself, implying, and that's the heart of the argument, that either this plane is age n or this plane is age n. One of the two half-planes that defines the lowermost vertex. In two-dimensional, to define a vertex, I need two half-planes. Only two of them are special. Thought about them as the maximum or the minimum in the exercises that we did last week. Two half-planes are special. At each iteration, we pick one of the half-plane and insert it. All permutations, as we said, are equally likely. Each and every permutation is equally likely. What is the probability that I picked a permutation for which one of the two red half-planes, and the two red half-planes are property of the problem. They have nothing to do with the order. I look at all the half-planes, look at the lowermost point, it's on two half-planes. Let's call them spatial. These are the two red ones. I pick a random permutation. What is the probability that the last half-plane, the nth half-plane, is either this one or this one? Only 2 over n. Okay, so the probability that we picked one of these special half-planes in the last case is the probability that Vn is different than Vn minus 1 is only 2 over n. Or if you prefer the backward a way of looking at it, I inserted all the half-planes and now I pick one and I remove it. What is the chance that the one that I'll remove is one of the two half-planes on which Vn lies? There are only 2 of them. That's why the probability is only 2 over n that I pick as the very last half-planes, that I pick one of the special ones. Right? Think about it as here is a set of all my half-planes. 2 of them, I know that they are special. They determine the minimum, but being the special or not has nothing to do with the order that I pick them. All permutations are equally likely. That is, as we'll see when we'll talk about how to generate a permutation, when I'll pick a permutation, this one has the same chance to be the last half-plane that is inserted as this one or this one or this one or this one. That is, for this half-plane to be the last one, the probability is 1 over n to be the last one, because it has the same chance to find itself as the first, as the second, as the third, all the way up to the last one. And this one has the same probability of 1 over n to be the last one. And only if I picked one of these two guys to be the last half-plane to be inserted, only then I need to work a lot of time at the nth stage. So let's make it a bit more formal. And if now I'll denote a new random variable, xi, and xi is 1, it's a Boolean random variable. Xi is 1 if vi is different than vi minus 1. That is, if in the ith step I had to call 1 LD we set or we define random variables x3, x4, x5, dot, 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 xn. These are all random variables. And now I pick some random order of defining the half planes. I pick some order to define the half planes. And I'll set that xi, this flag is 1, the ith flag is on, if and only if vi is different than vi minus 1, which means that in the I stage I had to call 1DLP, and otherwise xi is 0. What is the overall? Now, let's assume that I pick the order of insertion. How much work did I spend for the whole algorithm? It is sigma. I goes from 3 to n of 1. I have to do 1 work no matter what, just to check if vi minus 1 agrees with hi. If vi minus 1 agrees with hi, I spend a constant time, plus if xi equals 1, how much work do I need to spend? When I'm calling the one-dimensional linear programming, it's linear in the number of half planes that I have at this moment. That's the ith half plane that I have at this moment, which is j. So it is xi times I. It will cost you a constant. I ignore the constant. There is some constant here. That is sigma of your spanning 1 plus if xi equal 1, then you have to spend ith work. And if xi is equal 0, which is hi agrees with vi minus 1, meaning that vi minus 1 and vi are the same variable, then xi is 0, right? If vi equal to vi minus 1, xi is 0, and then I don't need to spend any work. And this expression tells me what is the running time once I know the order of the insertion already. The moment that I define the order of insertion, this expression tells me exactly how much work I have to spend. So, quick example. Let's say that this is the order. So this is age 1, this is age 2. Age 3, age 4, age 5, dot, 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 age n. How much work do I need to spend if this is the order? Help? Oh, let's start even a step earlier. What are the values of the xi's in this case? Maybe somebody from the silent ones, the ones that I usually don't hear. At each iteration, my solution started V2 was here. I insert V3, my solution would be, say, here. Inserted H4, I need to update my solution, and each time I need to call the one-dimensional linear programming. And so xi are all ones, and then you're just getting the sum of 2 plus 3 plus 4 plus 5 plus ... n, which is n squared. Correct? On the other hand, if I start where this is age 1 and this is age 2, and this is my optimum solution, then age 3 agrees with this optimum solution. Age 4, age 5 all agrees with this optimum solution, so all the xi's are 0. Everybody's happy? So the moment that I told you xi just says xi times I is the actual running time that you're spending. Now we are looking at the average if we are repeating this experiment million times. I'm not changing between time to time. I'm not changing the input. The input is the same input, and you, with all your natural viciousness and all your bad intention, told me what are the half planes that I have to use. You're trying to create the worst input for me. And the only thing that I can do to handle your mean intention is just to pick different random permutations, or maybe average or overall n factorial possible permutations. Same thing. The input is bad, but I repeat it when the randomness here is not average input. The input is the same. The average here is on random permutations, random order of insertions. So I will ask now not what is exactly this sum, because this sum depends on the order, obviously. I will ask what is the expected value of this sum. This is the average running time. Right? What is the expected value of this expression, which is a running time, over all the permutation, or over repeating the experiment with the same set of half planes, but you're making a new random choice at each iteration. Yeah, so we saw this part. So the running time of this algorithm, there is a constant at each iteration, so it will contribute 1 per each iteration. And what I really want to know is what is the expected value. Sometimes we will use a fancy E to denote the expectation, like E with 2 lines over here to denote the average value of this expression sigma of I times xi. Xi is a flag 0 or 1. I had to call the 1 DLP, or I didn't have to call the 1 DLP, possibly at each iteration. So what is the expected value of the sigma? What did we say about 2 variables? The expected of the sum is the sum of the individual expectation. E of x plus y, when there are 2 random variables, is E of x plus E of y. That's always true for any random variables, not necessarily Boolean. And again, I don't care at all how they relate to each other. If they are describing events that always happen, sometimes happens, I don't know. This will always be true, and I just had a this will always be true, which of course implies that E of x plus y plus z, 3 random variables, is just E of x plus E of y plus E of z. If there are 3 of them, you can look at the individual sum. Or in this case, I have sigma of n minus 3 such random variables, x3, x4, x5, all the way up to xn. And if xi is 1, then I need to spend I time at this stage. I'm looking at the expected value of the sum. Expected of sum is the sum of the expectation. Right? Let's do it. E of sigma of I times xi is just the sum. I switch the E and the sigma. The sum over I goes from 3 to n. It's I goes from 3 to n of E of I times xi. Expected of sum is the sum of the expectation. What did we say? The I here plays the rules of the constant A in the previous slide. So I can take the I and write it before the sum. So this is sigma of I times the expected value of xi. I goes from 1 to n. This is a Boolean random variable. It's either 0 or 1. And what did we say? That the probability of xi equals 1 is 2 over I. You are xi is 1 only if the last half plane that I inserted is one of the two special ones. And as you can guess, when we'll talk about three-dimensional linear programming, instead of 2, it will be 3 over here, or D in general. So now I have I times, what did we say is the expected value of a random variable? It is either 0, it is E of xi is 0 times probability that xi equals 0, but since there is 0 here, I don't care, plus 1 times probability that xi equals 1. So all that is left from here is just the probability that xi equals 1. So this is sigma of I times probability that xi equals 1, which is sigma, as usual, I goes from 3 to n, of I times, what is probability that xi is on, the flag is on, it is 2 over I, which is sigma of 2. I goes from 3 to n, right? So this is 2n. And that's a completely formal proof. That's I didn't cut any corners. So the average running time of the algorithm is only linear. And with a bit higher mathematics, you can actually prove that the probability that you'll be unlucky in the permutation, probability that you'll be far away from the optimum, is exponentially small. You're much more likely to be near the optimal, near the average. That's the average running time, but you are very likely to be very close to the average and much more unlikely to get closer to the n square term that might appear but with very low probability. Okay, so overall the permutation is just 2 over n. And we are close to the end of the linear programming algorithm in 2-dimensional. One thing that I owe you is how to generate a random permutation I want to generate a random permutation in an array, and of course I want to do it quickly. It shouldn't be the bottleneck of the algorithm, so I want to do it in order and time. If it takes me too much time to generate the permutation, just generating the permutation is the bottleneck, so it doesn't help me that the algorithm is it doesn't help me that the algorithm is fast. But if I need to start the algorithm by mess up the order, and I want to make sure that every permutation is equally likely. Again, I want to make sure that every permutation is equally likely. So here is an array A. Right now, that's how the user gave me the values. There is half plants, age 1, age 2, or something inside each cell. I don't care what are written inside each cell. And I want to work on the very same array. I even don't want to waste the memory of another array, but I want to generate a random permutation. So the algorithm goes as follows. So pick k at random between 1 to n. So this element is 1, 2, all the way up to n, and I pick element at random between 1 and n. That is, if my random variables, if R, A, and D, the random variables that you have on your computer, returns a number between 0 and 1, I'll take this number between 0 and 1, multiply by n, which is the side of the array, and if it's between 0 and 1, and I take the ceiling because I need it to be an integer between 1 and n. Okay, so it's rand, open parenthesis, close parenthesis. In most languages, that if it rand gives me a value between 0 and n, times n. Voila, this is some index over here. This will be k. And that will be the last element that is going to be in the permutation. It's going to be the last element that is going to be in the permutation. So the next step is swap a k with a n. So I swap a k with a n, or just output a k, write it to an outside array. Help, what do I do now? Exactly. So to go through the bad strategy, if I would have written AK to an output value, I should have marked somewhere not to pick AK again, because I already picked it. And as time progressed, if I just mark which cells don't take again, then suddenly you have a lot of choices that hits elements that you already picked. So the clever idea is, not mine unfortunately, the clever idea is put AK as a first one, and each element has the same chance to be the ones that you are placing at AN, but including possibly the chance that you started with AN and you don't move it. Each one of the elements have the same chance to end up right here. And now I'm only picking an element from this side all the way up to n minus 1, so I'll do n minus minus and go to pick another number now from this array and replace it. Pick an element from this side and replace it with a n. Put it over here and do n minus minus. And you stop, of course, when you got to a1. And you see that every element has the same chance to be the first one. Every element has the same chance to be the last one, which is exactly what I needed. Everybody's happy? And I already gave you this spiel, but because I'm so impressed, it's an algorithm that started as nobody knows if it has a linear time algorithm at all. And log n people knew long time ago. Linear time algorithm was a big challenge, was a huge breakthrough when it came up. Very slow algorithm in practice, very, very hairy analysis. And now we are using here a 3-line algorithm that all of you can easily implement. Practically is very fast in practice, and all of you understand the analysis. And just because this fantastic trick of the backward analysis that explains the justification. That at every moment there are only two special variables, two special hyperplanes that are important. Let's talk about linear programming in 3D. Going very similar. So now the input is a collection h1 ... hn, but they are not half planes, they are half spaces. What is a half space? Half space is everything that you can write as alpha xi plus beta y, alpha x plus beta y plus gamma. We'll say that this is large or equal than z. Then there is some half planes that you cannot write. This alpha x plus beta y plus gamma equals z is give you a lot of the half planes. It's analogous to alpha x plus gamma equals y. That's what we had in 2 dimension. What we had in 2 dimension to design a line, or the more general part of writing a line was to write it as alpha x plus beta y plus gamma equals 0, because that's way I can also generate vertical lines. In this form I cannot generate vertical lines, and to make it a half plane I'll just replace it to be large or equal than 0. And if you want the other side of the half plane, just multiply alpha, beta, and gamma by -1, and you're getting the same side of the very same half planes. So here the specific way will be alpha x plus beta y plus gamma larger or equal than z, or alpha x plus beta y plus gamma z plus delta equals 0. So there is some redundancy, but I'll use 4 variables, just analogous to 3D. This is a plane in 3D. If you like linear algebra, you know from graphics, for example, that you can write a plane as all the vectors x such that n times x minus a equals 0. where n is a vector or nx equal na. N is a normal, n is just a vector alpha, beta, gamma. If you prefer this way to handle half planes, or can write them as n times x, n dot product x equals b, where b is a scalar. Or we can just treat the half planes in this way. There's alpha x plus beta y plus gamma z plus delta equal 0. So a half plane is the same, just replace it with large or equal. Now Li, just to recycle the same notation, is a plane that bounds hi. Okay. What we had earlier was hi was half planes and Li were lines. So I want to use the same notation, so Li now is a plane, and the plane that bounds the half space hi. V3, that's where I start the algorithm, is the intersection of the three planes L1, L2, and L3, analogously to started the linear programming by picking H1 and H2 and takes the intersection point of their planes and called it V2. Now I'll start by intersection of two planes defines a line, cross it with another plane, you'll define a point. So now V3 is the intersection of the plane L1, L2, L3. And I insert the half planes at a random order, H4 dot 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 Hn. Before I insert them, I run the algorithm for creating the permutation that we saw earlier. I didn't say it specifically. The running time of this algorithm to generate the permutation is of course linear, right? There are exactly linear many steps to generate the permutation. So I insert the half planes at a random order. At each iteration, Vi is the optimum. It's completely analogous to what we did in 2D. And now we check. If Vi minus 1, the previous optimum solution, now these are half planes, age 5 is here, and this is V5, and here is age 6. Age 6 does not violate V5. If it's not broken, don't fix it. So if Vi minus 1 lies inside hi, there is no violation, then Vi is just Vi minus 1, and it just took constant time to validate that this is a case, that there is no violation. Otherwise it's really interesting. What do I know otherwise? Here is age 7. Here is age 7. It violates hi. What do I know about the new optimum solution? What do I know about the new optimum solution? I have to pick a new optimum solution. But what do I know about the new optimum solution? It must lie on L5. The new optimum solution, the new V7 must lies on L7 on this case. Right? Remember the proof. If it's not on H7, let's say that this is V7. Half planes are also convex. Let's move from V5 or V6 into V7. Actually, let's move in the opposite direction. V5 is always better than V7 because the more constraints that we have, the less optimal it becomes. And if I start following the line, let's say that V7 is not on L7, the plane L7, remember L7 is a plane right now, as I'm walking my way, here I'm inside, V7 is inside edge 7, V5 is not on edge 7. As I'm walking down, I'm improving my cost function, and at some point, since here I'm outside, here I'm inside edge 7, here I'm outside, at some point as I'm walking along this segment, I must cross V7, the boundary L7 directly. So what do I do if it is on this half length? Look what happens. What did we do in the two-dimensional case? We had to call linear programming in 1 dimension. Now we are in 3 dimensions. But look, I tell you that the new solution doesn't lie anywhere in space, but it must lie on the plane L7 itself. So now it's linear programming in 2 dimensions. So my code calls linear programming right now in 2 dimensions with which constraints? It's 2-dimensional linear programming with the constraints edge 1 intersected with Li. It's a half plane. Well, we think about Li as, it's a plane, it is arranged strangely, but as far as it knows, Li is just the whiteboard. It's the same plane as before. And inside this plane, Li intersected with edge 1. I take Li, I intersect it with one of the other half planes. I intersect it with one of the other half planes, hi, which now implies that everything, say, below my finger, is inside edge 1 intersected with Li. It's just a 1 dimension, it's just a half plane, right? Because on Li itself, Li intersected with L1, it's intersection of 2 planes, it is a line. It is a line that lies on Li and on L1, and I'm looking at everything on one side of this line. That is, the code doesn't care at all that it's not the same plane that we had before, it's just arbitrary plane. So it's edge 1 intersected L1, edge 2 intersected L1, edge 3, and so on. It must be on Li itself, and you're just creating on this plane Li a set of half planes by intersecting it with all of the other constraints. So what is the probability that Vi is different than Vi minus 1? It's not 2 over n. It is not 2 over n, because now when I'm looking at the lowermost point, I think that my cat will not mind that we are using her box. We are looking at the lowermost point, at the intersect. My half planes are all the sides of the box. I'm looking at the lowermost point that is in the intersection, and it's not true that there are 2 special half planes that determine the lowermost point. It is 3 half planes. So the chance that Vi is different than Vi minus 1 is just 3 over I. Okay, so with pretty small probability, I need to call the 2D linear programming. And the 2D linear programming on one hand, on this hand, with pretty small probability, might call the 1D linear programming. Okay, makes sense to everybody? Okay, took much longer than I thought, but yeah. So let's summarize the 1D LP. So in general, in the D-dimensional, this code we can apply to every code, and it's linear in every dimension. The running time is linear. The LP takes the same algorithm, it's linear in any fixed dimension, but now we are getting into the curse of dimensionality. Which means that there is this unpleasant term over here that says that if you are going into higher dimensions, then don't use this algorithm, instead using the simplex. And simplex is the thing to go that is very easy for you to access. Maybe I'll give you a little exercise in Python or in MATLAB to do a couple of things with linear programming in simplex, and that apply the simplex algorithm, and that solves very large linear programming practically very fast. But it's not linear in low dimension as opposed to the solution that I just showed you. Okay, and our next topic is just to reinforce the same way of thinking, is finding the closest pair problem. I have a set of points. I want to know what is the closest pair among this set. Much less important problem, but it's a very cute implementation, and it will tell us a very important data structure that is very useful on its own right. So I don't mind going through this exercise, and it also demonstrates how the same analysis gives us a very fast algorithm in this case. Question, people? Okay. Go over a lot of new terms that we covered today. If it's new for you, we can set a time to rehash it further outside office hours if you want me to. Okay, better. Questions? Anything?